My talk today is about how to address the energy problem in sensor networks through node reclamation and replacement for sensor networks which need to operate for a very long time. First is a very brief introduction of sensor networks. So you'll know that technology advances has enabled integration of sensing, data processing, and wireless communication into a single customer node. And the sensor node is powered by the battery. So here is, this example is the Berkeley Micro 2 prototype. Because sensor node of limited capacity and they are very cheap, so generally a large number of sensor nodes are deployed in the target field and the monitor field. So after the sensors are deployed, they can self-organize through wireless communication into a network. And each sensor can monitor the area around itself. If sensor can monitor the area around itself. If some event happens, like see a forest fire, the nearby sensors can detect it and can generate alert signal. And those messages can be sent by hops through wireless communication back to the base station. So once the base station receives this alert signal, so a fireman can be sent to the spot and deal with this fire. So this is just one application of sensor networks. So from the application, we can see that a sensor node can conduct multiple tasks, sensing, data processing, wireless communication, and for mobile sensors, it also has these moving tasks. So all these activities are actually supported and powered by battery. So look at this battery. A battery has just a limited amount of energy. So once a sensor nodes run out of the battery, so all the activities must terminate. So they cannot function anymore. You can see from time to time, the energy are just depleted. So, and in the end, this is the problem. So the energy has been a fundamental concern for researchers in network design, and there is a lot of work on how to conserve the energy of sensor networks. So it's more like a common sense that sensors cannot be recharged. So because sensors cannot be recharged, and we need the sensor network to operate for some time, so the energy consumption has to be conserved as much as possible. And therefore, there are a huge body of research on how to conserve energy in sensor networks. So like the energy efficient mining protocol, energy efficient routing, energy efficient data aggregation, etc., etc. Well, however, if we look at the battery has only a limited amount of energy. So no matter how much effort we make to slow down the energy depletion rate, eventually a sensor node is going to run out of battery. And the lifetime of sensor network actually is just bounded by the capacity of batteries. So let's look at this picture. Two batteries. So each sensor node are powered by two batteries. So now, no matter how much research effort we make, a sensor node can be live for, a couple of months at most. But for many applications, sensor network is deployed to monitor the house, a building, or a bridge. This sensor network is expected to operate for a very long time, like tens of years or even hundreds of years. So this is a very sharp contrast, a couple of months or versus this tens of years. And this is the motivation of our work. What can we do such that sensor network can have a very long lifetime? Existing solutions includes environmental energy harvesting. The sensor nodes can harvest energy from the environment, like the sunlight, or wind, or acoustic variations. But this scheme has the problem, like the reliability problem, feasibility problem. So, for example, the solar cell. The energy efficiency of a solar cell is proportional to its area. So a sensor node is very small. It is kind of not feasible to equip each small sensor node with very large solar cell. And also consider when it is cloudy, and there will not be this energy source. Some other alternatives like incremental deployment schemes. So once the sensors run out of battery, we can deploy more sensors. And once these sensors run out of battery, we can deploy even more sensors. The problem of this scheme, not to mention cost, actually is the function problem. We cannot just deploy as much sensors as possible without reclaiming them, because there's really a serious function problem. So our strategy actually is the node reclamation and the node replacement. So suppose there is an energy station. The energy station can recharges the sensors without energy or with all energy. The energy station also has a lot of backup sensors there. And there is a mobile repairman. This mobile repairman can periodically replace the sensors. They can move to the working area of sensor network, collect the sensors without any energy, and replace them with sensor nodes with full energy. So certainly here we assume that the sensor network is accessible by this mobile repairman. So the mobile repairman can be a mobile robot. It can also be a human operator. Then the problem is, so how to determine the travel schedule of this mobile repairman and how to determine the duty cycles of all the sensors such that at any time the quality of service is guaranteed and also the system overhead is minimized. So this is our objective.
So you assume actually mobile repairman knows the location of the sensors.
Right.
And knows the energy how much power remains.
I will cover this thing.
Okay.
So the challenge of scheduling both the sensors and the MR is actually the scheduling of both are interdependent on each other. So when the mobile repairman comes and replace sensors determines how the sensors schedule their duty cycles. And also how the sensors schedule their duty cycles and how they run off their battery power determines when the mobile repairman should come and replace them. Actually, they are independent of each other. So this is the challenge. And also this is an online problem because we don't know. So what is the energy depletion rate of sensors in the future? We don't, if there are a lot more events, maybe sensors can be in the on state for more frequently. Otherwise, they can be in the sleeping state more frequently.
So when you say duty cycle, it's
on and off.
On off.
Sleep or wake up. Yes. Yes.
The mobile will only come with the noise not on duty. Do you mean that the repairman will only come with the noise not on duty in this hall?
I will cover that. I will cover the further in our slides. Okay, so our general idea to solve this problem of interdependency is, so we propose this adaptive, rather based two-tier scheduling. So in the global tier, it is determining when and where and in which sequence that the mobile repairman should visit all the sensors and replace them. And in the local tier scheduling, it is sensors. They determine when they should be on and when should be off. And here is a appointment point. And in this appointment, so this is more like a deadline. So the sensors, they have this deadline. So they know that I have to be alive until that deadline. And for the MR, it knows that by that deadline, I must visit the sensors and replace them. So before I present the detail of this art scheme, let me just describe the system model. So first is the assumption. We assume there are enough supply in the energy station. And we will not consider any cost issue here. We just assume that there are enough sensors. And also, the mobile repairman has a capacity C. That is, each time how many sensors it can carry. In our system, all the sensor network is divided into groups. This work does not.
The mobile repairman capacity
how many sensors it can carry. It
So
can
it carries just the
It carries the good
sensor
sensors
equipment.
and go there and replace with the bad sensors and then go back to the energy station. Okay, so here we're not concerned about the details of the connection, communication connectivity, sensing coverage, etc. We just assume that the sensor network sensors are divided into groups, and in each group, a certain number of sensors need to be active. We call it surveillance number. And this number will be vary from Nmax to Nmin. So we can see that at any time the application requires at most Nmax number of sensors to be alive. So if Nmax sensors are guaranteed to be active at any time, then all the application level requirement can be satisfied.
So actually, you don't care where these Nmax sensors are deployed as long as they're this number?
Right.
But what if they're just clustered together, but all the other areas actually are not covered? Will that be an issue?
Coverage is another problem. So if the sensor if the field is not covered by the sensor network from the beginning, it will not be covered later. So we just assume that.
Okay, what I mean is maybe you have a total of M sensors, right? They can cover the field.
Okay.
But now you're saying if N max of them are alive, then the quality of service is ensured. But I think it's not only the number of active sensors, but also where they are, like how they're positioned with respect to each other.
Yeah, I agree. Well, here is just abstraction.
Okay.
And this is, well, it also depends on how you divide them into groups. This group can be very small.
Oh, okay, so here.
And also like
associated with a geographic area to say, oh,
Yes.
this group is responsible for this area here.
Yes. And later we'll talk about
So why isn't it Nmin? Why is it Nmin needed? This small Nmin number are.
certainly Nmin can be 0.
Oh, and then can be anything.
So
Nmin can be 0.
So when you say, oh, you need a certain number to be active,
Yes.
that sounds like the minimum number to be active to guarantee.
Oh,
I think
well,
Nmax
this is more like an online problem. Now,
Yeah.
maybe you just need one sensor to be alive. Maybe in another day you need 5 sensors to be alive.
I see what the math is, but it's Yang Yang says it sounds like Nmax is the minimum, so why isn't Nmax, the thing you're calling Nmax means
I
all
think
that
Nmax is, see the application, suppose, for example, the 10 coverage, any point will be covered at least 10 sensors. Is what the application will, it is the highest requirement from the application. Then we call it, say, Nmax is 10, for example. So the application will not require more than that. Okay. So if we can guarantee that, because we don't know in the future what application will require, so if at any time we can guarantee that there are Nmax number of sensors alive, then we can guarantee the quality of service. So this is an abstraction of that because we are not concerned about the coverage or activity, etc. So this is just about scheduling. So then the objectives are, see, at any time the Nmax sensors must be alive to ensure the sensing quality, and also the moving distance of the MR is minimized. So these are the 2 objectives which need to be satisfied at the same time. Okay, so here is the general procedure of this ARTS scheme. The local scheduling is about how the sensors do the duty cycle scheduling in each group. And the global tier scheduling is for the MR to determine in which sequence and what time to visit each group to replace and reclaim the sensors. And the whole procedure goes round by round. And in each round is divided into phases. So you can see here this is one phase, and this is one round.
So a group is a geographic group. You say a group of sensors, is it a geographic group or?
Yeah.
Mm-hmm.
Okay, so in each round, the mobile repairman will visit a group, and it will reclaim and replace the sensors, and also it will collect the remaining energy information of all the sensors in this group. So upon this point, the mobile repairman will have this energy map of this group. And then the mobile repairman will notify the sensors of its next visiting time in next round. So by giving this appointment time, the sensors can conduct this local scheduling such that before the mobile repairman comes, okay, we can guarantee the contact service. That is, we can guarantee there are at least a max number of sensors alive. And after the mobile repairman returns to the energy station, the mobile repairman has collected the energy information of all groups. Therefore, it will calculate the number of sensors to be reclaimed in next round, and its visiting time in round G+2, which is just the round after next round. And then in the next round, the mobile repairman will visit the group again, same as this procedure, and then notify the sensors of its next visiting time, which is calculated here, and also reclaim sensors. So this is interaction of this global scheduling and local tier scheduling.
So in each round, each group is visited once. So in a round,
it's determined.
We
need to calculate how many sensors need to be reclaimed. If it's 0, then in this round the mobile sensor will not come. The mobile robot will not come.
And how long do you think it'll go?
Okay, before round J+1, how does the mobile requirement to calculate the next visiting time? Or how does it give the sensors that when I will go to, I'm going to visit you again?
So you mean here?
Yeah, every round. For the next visit time, how does that requirement to calculate?
Oh, so this is the global tier scheduling work.
So
the global tier scheduling algorithm will calculate for the mobile repairman then when they should visit and what is the sequence.
So it will be different for each group? Or
well, definitely it will be different. You cannot visit two groups at the same time, right?
why not? You can go a long way and save your energy.
Oh, no, I don't mean that the mobile repairman visit one group and they go back. It is visit one group, then the other, and then the other, and then go back.
So it will only take several minutes to visit each group. So there is no difference between each group, right? Like the repairman visits the first group, then after several minutes it will visit the next group.
Well, I think it depends. It depends on the location, for example. First of all, maybe these groups are not very close with each other. And also it depends on so this is all the mechanical movement. I need to this is a mechanical arm. I need to grab the sensor and put another. This takes some time. Certainly, we are not concerned about the details.
You're going to talk about the calculation of the schedule time.
Right.
Okay, so I have a market question.
Uh-huh.
What if the number of sensors needed to be replaced is greater than C? In that case, what's the decision? Like, you only replace C or you replace?
Then it is not it is not a solvable problem. So certainly you can divide the groups, divide into smaller groups, so such that at each time at least you can replace.
So is C the number of sensors you can replace in a group at a single visit, or is it the number of sensors you can replace?
No, C is the capacity. So for example, the mobile repairman can carry 100 sensors, but for each group they just replace 5.
So that's the number that you have per round for replacement? Like a round, what you call a round J, round J. You visit multiple groups in one round.
Actually, how many groups they visit in each trip is also calculated by the global tier scheduling.
So you visit multiple groups in each round.
Right.
So
well, in the extreme case, it's going to visit just one. Suppose if the capacity is very small.
Yeah. But C is the number of sensors you can replace in a round, not the number of sensors you can replace in a group.
In a round. How many they can carry? This is the sensor. How many sensors a robot can carry? Yes.
Does the mobile repairman always visit groups in the
No, it depends. Well, it is calculated by the local tier scheduling. Yes.
When the sensor nodes conduct local scheduling, it seems like they need the time that they're going to be visited next, but you said they might not be visited in the next round?
They're going to be notified. See here, they're going to, so here, this is the end of round J or the beginning of round J plus 1. They're going to calculate the visit time in round J plus 2, which is the next round. So, no, the round after next round. So when the mobile repairman visit, he's going to well notify the sensors. So the sensor knows that.
But
So basically, the visiting time actually is this apartment.
Well, what if he doesn't visit that group?
This is a detailed question. Actually, based on the calculation in the next round, they're not going to visit the sensors. That means they're not going to have the residual energy information of the sensors. Then they are going to calculate the visiting time and the number of sensors in a very conservative way. Okay.
So the energy used by a sensor between visits is a random variable?
Yeah, it's a random variable. It's a random discrete variable here, based on the abstraction. Okay, so the local tier scheduling. The objective is given the MR's next visiting time, so how the sensors can coordinate and guarantee that the contact service for any phase before the MR's next visiting. And the other objective is how to minimize the residual energy in sensors to be replaced. So why we have this objective? So consider the sensors to be replaced. No matter how many energy left in those sensors, those energy actually wasted. So we try to replace the sensors without energy. We don't want to replace sensors with high energy remaining. So this is the objective. And the system model is at the beginning of one phase. All the sensors in a group just wake up and take part in the scheduling. We assume there is one, cluster head or group head. And this one received the command from the application and determines in the next round how many sensors we need to be awake. This number will be smaller than Nmax or equal to Nmax, and be larger or equal than min. So each sensor received this message. They are going to independently run the local tier scheduling algorithm. So here we assume all the sensors in the group knows their residual energy level of all their neighbors. This can be done throughout the broadcast. Well, the philosophy of the scheduling algorithm is we try to overuse sensors with least energy level. So such that the residual energy in sensors to be replaced, to be reclaimed is minimized. Well, based on this philosophy, the natural algorithm is just this greedy heuristic. So if we look at this picture, so there are 7 sensors in the group. And this number is the remaining energy level. So these 2 sensors have 5 units of energy, and these 2 have 1 unit of energy. So the MR will come 3 phases later. And suppose a sensor will consume just 1 unit of energy per phase. And we assume that Nmax is 5, and it is a required surveillance number. So if we just conduct this greedy heuristic, so in the first phase, we'll have these 5 sensors work, and this is the energy level after 1 phase. And we also schedule. Note that these 2 sensors already run out of energy. So these 5 sensors will be scheduled, and this is the remaining energy level. And now there are only 3 sensors alive. So we will find a failure. So the heuristic, the greedy heuristic does not work.
Why doesn't it work?
Oh, the Nmax is 5. That means for all the phases, we must have 5 alive sensors. But if you schedule them in a greedy way, after 2 phases, you have, well, all of these 4 sensors run out of energy, and you only have 3 alive sensors. So this is the problem of the greedy.
Is there an alternative? Like it only fails if in fact there was some alternative approach that keeps them alive. It seems like your problem is an infeasibility issue, not that the greedy heuristic is bad.
Well, you can use the other 5 all the time.
Which other 5?
Okay, so I think there's a
Well, certainly you can always schedule this one. But the thing is, we try to minimize the energy level of sensors to be replaced. So therefore, we try to overuse these sensors. So we hope, suppose this 4 sensors are to be replaced. We hope they have no energy. We don't want all these 4 sensors still have some energy, and this 3 sensors also have a medium energy level. So this is not the best case.
The dashed line, what does it mean? Like in each graph, you show the dashed horizontal line.
that's the
Oh, I see.
What does that mean?
Well, that means I just copied from the paper. I don't want to restore the figures. So actually, this line means if whether or not. So if this bar is above the line, that means if I'm scheduled for all the consecutive phases and until the MR comes, I'm still alive. If I'm below the bar, then I cannot achieve that. For example, for this one, I have 5 energy unit, and the MR comes 3 phases later. So if I work for the whole 3 consecutive phases, I'm still alive. But for these sensors, they only have 1 unit, they only have 2 units. So they can only work part-time for the next several phases.
So the sensor is okay as long as its bar is not 0.
Right. But the thing is, this one may still be okay, because if there are, say, 5 consecutive phases, and this one only need to work for 1 phase, it's still alive.
So basically, I guess I'm a little confused. So both the solid bar and the diagonally dashed
So this
shaded bar, the
this
shading
may-
indicates which ones you're using.
this one means I'm going to schedule these 5 sensors to be awake, and these 2 go to sleep. And this is these 5 sensors to be awake, but these 2 are dead anyway.
So why this is greedy?
Why this is greedy? Because the philosophy is
you punish the
right. We
least
just try to
radiation energy.
overuse the sensors with least energy, because we don't want the sensors to be replaced. Still has some energy.
So that means each group want to replace any sensor possible.
No, the number of sensors to be replaced is calculated by the global scheduling. It will be notified by the sensors will be notified of that information.
So did you formulate this as an optimization problem, the local peer schedule?
Actually, it is.
Because I'm having trouble understanding, is your optimization to maximize the number at some future time that have a certain level, energy level?
Well, if you look at the whole problem, this is an online optimization problem.
Well, but we have a sub-problem here.
Right here, the some problem is given when the mobile repairman will come. So how to schedule that how to schedule it such that these 2 objectives are satisfied? Yeah, it's an optimization problem. And we may have a fixed answer. So. Question? Okay. Okay, so the greedy heuristic does not work all the time. So we discovered this guard inequality. So the guard inequality becomes the guideline to design this local tier scheduling algorithm. So basically, it is the satisfaction of the guard inequality guarantees that. So if a duty cycle scheduling algorithm, a duty cycle scheduling can be found for the current phase and satisfying the objective for all the subsequent phases, is also satisfied. So here I'm not going to talk about the proof, but the proof is in the paper. So the general idea is, suppose there are n number of sensors in the group, and based on their remaining energy level, So we are going to sort them into a list. See here, this group has 7 sensors. We sort them based on the remaining energy level. So for this sensor, it has 5 units, and this one has 1. So we are going to divide this list in 2 lists. So for this one, this is L1. So that means for all the remaining 3 phases, they can be up all the time. They are still alive. For this 4, so that means they cannot be up all the time. Otherwise, they're going to die. So we just divide this list into 2 lists. And the guard inequality is this way. So if we just sum all the remaining energy of these sensors in R2, and if this number is larger than this number, then we can guarantee that for all the subsequent, for the current phase and all the subsequent phase, the optimization problem is solvable. We can find one. Okay, so the intuition of this inequality is, so the sensors with low or no energy, so should not be overexplored, even though they should be overused, but they should not be overexplored, in order to keep the total number of alive sensors to be greater than a max. So this is our objective. Okay, so here's the algorithm. So this algorithm is based on this inequality. So, and this is a step-by-step process. So in the step 1, we just conduct greedy scheduling. We just schedule all the sensors with the least remaining energy. So after we do that, we're going to check whether the inequality is satisfied or not. So if not, then it fails and go to step 2. For the step 2 is a semi-greedy scheduling. So for the semi-greedy scheduling, it is we are going to schedule at most this number of sensors in this list, and all the remaining sensors in this list. So if we look at the same example, so in the first phase, so instead of schedule all these 5 sensors with the least remaining energy, we only schedule 2 in this group. So Nmax is 5, M is 3, so here is 2. And we are going to schedule the remaining 3 sensors in this list. So this is the first phase. And this is the energy level after the first phase. And we are going to schedule this 5. And we are going to schedule this 5. So when we are going to see that at the phase number 1, okay, we can still have 5 alive sensors. And this is when so at time 0, so when the mobile sensors come, then, well, they are going to replace these 4 sensors with, yes.
The algorithm looks pretty complicated, but it looks like the same as consuming the energy which has the most remaining power. Is that identical or not?
I didn't get you.
So the simple algorithm that consumes the energy from the sensor which has most energy. We comparing to those algorithms, are they going to be different?
Yeah, absolutely, it's different. If you look at this algorithm, you're going to see that. So for the greedy one, you just schedule the sensors with the least remaining energy. This is this 5. But for our algorithm, based on this guard inequality, we're going to schedule this 2 and this 3. So this is not greedy. Okay, so here is the algorithm, and which is based on this guard inequality, and it is actually a very lightweight algorithm. So for this inequality, it's just the summation multiplication. You just need to check it. And for each phase, there is only about 2 steps. Basically, you just need to do some very simple calculation to determine which sensor should be on, which sensor should go off.
So what's random in this? What's random?
Well, you don't know. So here, to illustrate the algorithm, I assume that the application requires 5 alive sensors. But the truth is, maybe in the next round, the application will just require 3 to be alive. say for example, if this is the case, then the gradient heuristic works, because at any time you just require 3 sensors to be alive.
But the actual, when you leave the sensors, right, the actual energy consumption until the next time you visit doesn't appear to have any randomness.
Oh, so here we just use some abstraction that if the sensors are off, they're not going to consume any energy. But the sensors is on, it's going to consume 1 unit of energy per phase.
Yeah, so it's not random. So if it's on, it consumes.
If you, well, it's I think it's random. It's 1 or 0.
No, because you chose whether it's 1 or 0 by you control which
Right,
are
right.
1 and which are 0. It's deterministic by your choice.
Yeah, it is determined by the algorithm.
So it's not like, oh, when you decide to leave these 5 on, they have some, in a sensor network, you decide you're going to use these 5 sensors. Exactly what they have to do until the next time you visit them is typically random. It depends on what they measure. Do they need to transmit something? Do they need to exchange some messages to come to an agreement about an observable? There's a lot of randomness.
We are not concerned about that. So we just make an abstraction that, of course, the paper is, the talk is about the scheduling. So we just make an abstraction that if they are on, this 1 unit of energy consumption, otherwise it's 0.
I think I time 2. You can still choose the 2 with energy capacity of 2, right? If you choose 2 and at t equals
Okay,
to
at the time t equal to 2, you have no choice because you only have 5 alive.
No, if you use t equals to 3, if you use 2, then what you left is 5541111, right?
Okay,
That's what
no.
you have to see for real algorithm. No.
Okay, so for this, at any time you need to schedule 5 sensors, not 2 sensors.
Oh, I know, but at t equals 3, if you choose 55422, then what left is 4431111, right?
Right.
So at t equals 2, you can still use 44311, and next time 44.
Then this is not gradient heuristic.
No, not. But I said if you're in the next algorithm.
I think it's the same. Well, the results
So
will be the same.
yeah, the result is the same. So there is some randomness there. You can choose any of you can choose.
Well, certainly there are many ways to choose which sensors to be on. I talk about this algorithm because based on the inequality, we can guarantee that until the end, for all the subsequent phases, you must be able to find one.
But as long as you choose the first 3 with the highest energy, then you can succeed.
Well, this is just a special case. For this one, I think what you told me works. But for a more complicated case, you cannot guarantee that. But for this one, we have the proof in the paper, but we don't want to go through the details. Okay, so so the global tier scheduling. So here, the objective is given the amount of residual energy in each group. So which basically is more like the history, how the sensors use the energy, and determines how many sensors to be reclaimed for each group, and the travel schedule. The travel schedule basically means in which sequence and what time they should visit all the groups. And the objective is minimize the travel distance of the mobile repairman and also minimize the residual energy sensors to be reclaimed. For the second objective, which is actually the same as in the local tier scheduling algorithm, we don't want to reclaim sensors with a high energy remaining. Okay, so 2 subproblems. For the first one, we use this equation to determine the replacement numbers. I don't want to go into the detail of this equation, but the intuition behind it is we are very conservative. So we just assume the worst case, and in the worst case, how many sensors need to be reclaimed, and we just use this that number.
In what sense do you have a worst case? What do you mean, like we assume the worst case?
Well, consider for that, in the first round, we just assume the max. We just replace the max because we don't know. Well, in this round and the next round, what is the energy consumption? We just assume that we have to replace this max number of sensors. And for later on, you can see that.
You know what the energy consumption is, right? Because you chose what sensors to leave on and what period.
But you don't know in the future how the sensor consumes the energy. It may be N max. It may be N max minus 1. It may be N max minus 2. It depends on, it is determined by the application.
You mean over time, round to round, the
Right.
value of N max that is the net?
No, the N max is only the highest possible requirement by the application. It is not the actual requirement. The actual requirement may be smaller than that.
But it's known at the beginning of each round what value of
No, it is
sector
not
coverage.
known at the beginning of each round. It's only known in the beginning of each phase.
A phase is inside of a round.
Yeah, a phase is inside the round. And the different phases may be different. And actually, in each round, a mobile robot is visit the group once.
So in a round, each group is visited once, but then and that constitutes a visit to one group as a phase. Well, you use the word round, and then phase is in the round. So phase is the time.
Phase is the time how the sensors schedule their duty cycles. So in the beginning, or see the time slot. So in this time slot I'm on, in the next time slot I'm off. One round may have the 10 time slot, and 5 time slot I'm on, the other 5 I'm off. And the visiting time of mobile requirement can be any time inside the round. It can be a continuous time. It is determined by the mobile scheduling algorithm. To answer the question?
So you solve a sub-problem that says, oh, I'll need this many sensors active in this next round at this group.
Well,
And then
so
the
when I
numbers
talk
given
about
to you use that inequality for total energy to say, oh yes, this is feasible. And I'll given it's feasible, I have a schedule where I then
no, there's
schedule them deterministically, and you say, oh, it's 1 unit of energy per unit of time on per sensor.
No, I think here are a lot of variables. I think maybe, we just messed up here. So there's one number, it is the number of sensors to be replaced and reclaimed. So when the sensor do the local tier scheduling, they don't use this input. They just use how many sensors the application required to be on. And that particular variable is not needed here. And for the number of sensors to be replaced, actually is calculated by the global tier scheduling. They're two different numbers. Okay, so, and it is calculated by these two formulas. Okay, so the next problem is given the number of sensors to be reclaimed, and given the visiting time in each group, given the number to be reclaimed, that's each group, and the MRS capacity is C. So how to determine the visiting time to each group in a round such that the travel distance is minimized, the remaining energy is also minimized. Well, if we look at these two objectives, so if we try to minimize the travel distance, well, this is one way to propose the heuristic. If we try to minimize the residual energy of sensors to be reclaimed, this is another way to propose a heuristic. I cannot see which one is better because this is an online problem. We don't know how the sensors is going to consume energy. So what is the actual surveillance number required by the application? So if we just try to optimize the first one, the intuitive solution is, well, I think it's just equivalent to this capacitated vehicle routing problems. So given the locations of the group and given the capacity, So the sum of remaining energy to be reclaimed could be the travel distance of the MR should be minimized. But the problem of this one is the remaining energy of sensors to be reclaimed of all groups be high. So for example, if based on this heuristic, the mobile repairman they visit, say, in this sequence, but maybe this group has very high remaining energy, but this group has low remaining energy. So maybe in that sense, we should replace this one first and then the second. Give this group some time to consume their energy. So the sequence determines the sequence of the mobile repairman with a different group determines what is the residual energy in the sensors. So another heuristic is trying to minimize the residual energy in sensors to be reclaimed. So we use such a data structure. So here is the group ID. This is different group. And for all the groups, this is one phase and this is one phase. Because the mobile repairman knows the local scheduling algorithm. So the mobile repairman can just simulate the local scheduling phase by phase until the end of the round. So, and then the residual energy is going to be plotted here. So what does this mean? But that means by this phase, this group is going to run off energy. But for this group, it is better. So at this time slot, this group is going to run off energy. So this table actually indicate a deadline for that group to be reclaimed and replaced. Okay, so the heuristic can be just distribute or sort the groups into tours based on the similarity of their deadlines. So that means the mobile repairman can, for one round, the mobile repairman can have multiple tours. It's going to replace the sensors once, twice, or 3 times, multiple times in one round. And in each time, it's going to reclaim, it's going to visit the groups with similar deadlines, such that the remaining energy is minimized. So here is the two intuitive solutions, the two intuitive heuristics. So our heuristic basically is a simple combination of these two heuristics. We deploy alpha and beta, which actually is the weight. And we try to minimize this one. We try to minimize this equation. And we also prove that this one is actually an NP complete problem. It is, it can be reducible to this BQ routing problem with time windows. So this is an NP complete problem.
In this problem formulation, you have an implicit assumption that the cost of the residual energy is much higher, or the cost of replacing a sensor with higher residual energy is much higher than the cost of traveling some extra distance, and the cost of extra time consumed by a repairman.
Well, the problem is we want to guarantee that the sensor network will provide the required amount of service.
So
Guarantee that the sensor network can what?
We want to guarantee that. We want to guarantee the sensor network operate for a very long time.
So it seemed like you had two different optimization problems, right? One was a minimize the energy collected, the residual energy in the sensors collected.
Right.
And the other was to minimize the travel of the mobile repair.
Right.
And both of them subject to some kind of feasibility constraints that the sensors are good enough for the task. So those are two different problems, right?
Right.
So which one is it? Are they both NP complete, or is it?
No, this is NP complete.
Which one is that? The finding the travel schedule?
Yeah, from the travel schedule. Yeah.
So, yeah, that's surprising. What about the other problem?
To be frank, we didn't prove whether this is NP complete or not, but I don't think so. Because basically this is you just sequence them, divide them into groups. Basically a sort. So I don't think this is.
It's not, I mean, it's not that you didn't prove your schedule. Your intuitive solution is the optimal solution. Are you sure you know for a fact that your candidate solution is?
Well, the problem is actually to minimize these two numbers at the same time. But it is hard to minimize them at the same time. So we just say, let's just consider each one.
That's not a well-formed notion to minimize both. I mean, if you want to minimize some combination of the two, like a linear A, I mean, that's okay. But you didn't say that.
Well, we try to minimize them at the same time, but it is not possible. So we have to get some trade-off. So in these two slides, one is we just minimize the first one, and this is we just minimize the second one. And finally, we just use equation of ascending weights. And we try to minimize this value, y. Okay, so this is the...
Sorry to interrupt. Didn't really understand why the decision would affect the lifetime of your sensor network. How does the schedule that you come up with affect the lifetime of your sensor network?
Well, for the lifetime of sensor network, to be frank, I don't think it's affect the lifetime of sensor network. So here we assume that, we try to gain infinite along sensor network lifetime. So the problem is only how to minimize the cost, minimize the overhead.
Whether you minimize the travel distance or whether you minimize residual energy has no effect on the lifetime or
well, one is we try to minimize the work of mobile repairman, and another is we try to minimize the work at the energy station. We have the sensors collecting back, we have to recharge them. So we also want to minimize those work. But we didn't explicitly express that cost here. Therefore, we try to minimize the residual energy, such that if we...
Can you think of an example where the cost of residual energy would be so high that it would be worth paying
Okay, so actually the intuition is just like this way. See, if you have 5 sensors, you can overuse one, and the sensor died. The other 4 is alive, and this time you just replace that sensor, and then you recharge one sensor. Or the other way is, well, you have 5 sensors, you use each of them 1 time slot, and then in this round, all of them pass for some certain energy level, and then you replace one, and that. Suppose they have the same energy level. You replace one and you get the sensor back. You have a cost of coming and going back. But the remaining energy of the sensor the remaining energy of sensors after reclamation is lower than the first case. And in the long run, the mobile robot has to come more often, and at the energy station, you need to recharge more sensors.
So all of the root thing of how it follows a route is the distances are all from root to root.
Right. So we have the distance from the energy station to each group, and also the distance between different groups as input.
Right, but the idea is the sensor drives to a spot that is the root J spot.
Right. Right.
And it goes to another
Right.
spot. So somehow the only thing that really matters, right, and at each group, right, there's some requirement that the number of sensors is some number, right? And I think what your bound showed is that the only thing that really matters is the total amount of energy in the collection of sensors. Is that right? The sum of all the residual energies has to be above some threshold, and then you know that there's some scheduling of the sensors in the next period.
Actually, eventually it is this way, but we cannot simply just minimize that one because they are independent. They are dependent of each other.
No, but all you need to keep track of is the total residual energy of the group, I think.
Right, right.
So, so I guess I want to understand.
Okay.
Go ahead, I'm sorry.
Okay, so this is the super 2 heuristic. So, well, this one is actually, well, try to minimize this value y. So based on the deadline table, this is this heuristic, based on this deadline table. We are going to distribute groups into super groups. So for each one, the mobile repairman can visit the sensor network multiple times, and then each time they just visit particular subgroups. And then for each super tool is further divided into m physical tools. So one physical tool means the mobile repairman leave the energy station and come back and get new sensors. So for how one super tool is divided into m physical tools is determined by whether the travel distance is minimized or not. And for each super tool, so the mobile repairman needs to return to the energy station for m-1 times. So basically, this is a multiple visiting. And also for this m physical tools, it is ordered such that the residual energy of sensors is going to be residual energy in the sensors to be reclaimed is minimized. So this is more like the step-by-step minimization. Okay. I think I kind of run out of time, so I'm going to pass this part. Actually, this is another scheduling algorithm with relaxed assumptions. Like we don't assume there are enough backup sensors in the energy station. So if all the sensors die in the similar time, then there is some problem. And also here, we don't assume that this is a simple point coverage model. We assume this is the coverage set model. But I don't think I have time to talk about it. I want to go directly here. Well, here I mentioned this is the other solutions for long-lived sensor network, but actually this idea is we come up with this ideas earlier than what I presented just now. I think about 3 years ago, we found out this is a wireless charging technology. So we think about how the sensor network can be recharged in a wireless way. And then we submit a proposal, but it was rejected because of the feasibility issue. So then we work on how about we just reclaim and replace the sensors. Last year we submitted a proposal again, and we found some reference that this technology is really feasible. We also ordered some devices to do the experiment. So this wireless recharging technology can be applied for sensor networks. The sensors can be recharged through these wireless waves if the recharger is, I think, at most 30 feet away from the sensors. And all the sensors in the neighborhood can be recharged in a similar amount of time. So this is an exciting new technology. And this is a snapshot.
Did you try that out? How well it works?
Yes, we tried. We do the experiment. We order a device and they're really charging sensors. So we think about this scenario. So this is a mobile robot, just move around and charge the sensors in the neighborhood. So for both, so here are some discussions. I think for both wireless recharging technology and this node reclamation and replacement schemes, they both have limitations. Well, we require that the sensor network is accessible by the mobile robot or the wireless charger. So otherwise, the energy problem is still a problem. And also by employing the node reclamation or the wireless charging, the sensor network design will have a fundamental change because previously we tried to balance energy consumption. We have this, if we can route certain messages, we have shortest path. We don't want to overuse that path. We want to spread out, well, the tasks among all the sensors. But now seems we should just overuse certain sensors, and those sensors can be reclaimed, or the sensors can be recharged. And also for the node reclamation only, we need to think about how to keep the current state, because sensors, they have applications running. Maybe they already have some, say for example, keys in the sensors, and the keys have been updated. So once the sensor is reclaimed, certain information need to be transferred from the dead sensor to to the new sensors. This is also the work to be done. Okay, I think that's it. Any questions?